Okay, here we go on video 2 of Signal Integrity and Electromagnetic Compliance Training for Mere Mortals. My goal is to teach everyone in the universe how to design high-speed digital analog RF systems that work right and pass FCC CISPR tests on the first try. You got more information on siemc.com, and here we go. First of all, we're going to be talking about via impedance versus frequency and how that affects the return current. There are other topics that we'll go through. Right now we're going through the one in red, via impedance versus frequency and return current. So the first thing to understand is that when you put a signal through a via, i.e. I'm trying to change layers in order to accomplish some sort of crossover, that structure has got a frequency response characteristic to it. Now, what I've done here as an example is I've said, okay, here is a case of return current impedance with ground reference plane. So in other words, I'm looking at the impedance of running a via that goes from layer 3 to layer 6. So I'm trying to go from layer 3. This is an 8-layer board, so I'm going from layer 3 down to layer 6. So that's what this via represents. This via number 4, I guess that was number 3 in this case, but via number 4. And what we're looking at is what happens as a function of frequency as that signal tries to pass from layer 3 to layer 6. Now in this case, layer 2 is ground and layer 7 is ground. So in both cases, both on layer 3 I am referenced to ground, and on layer 6 I am referenced to ground. So now what we need to look at is what happens if I just have that via sitting in the middle of a board where maybe the closest ground to ground connection, is 3 inches away. And if it's something like that, then what I'll see is this purple response curve. So I've got an awful lot of stuff on the page at one time. The background here is impedance, so this is impedance in ohms, and on this scale is frequency. So I'm going on a log scale here. So 1 megahertz, 10 megahertz, 100 megahertz, 1 gigahertz, 10 gigahertz. And if I take this very first case, which is in purple, this is where the ground-to-ground via that ties that ground to this ground is not very close to the actual via itself. So in other words, here's the via, but I don't have any stitching via tying ground to ground anywhere close to this, and so consequently there's a frequency response curve to it, and that is this purple line. By the way, the tool that I'm using here is Mentor's Hyperlinks Power Integrity, and I'm using Line Sim in this case, but very nice tool, very nice tool. Now if you'll notice at about, I don't know, 920 megahertz or something, that via has an impedance pole or impedance spike that looks like almost 120 ohms. So this is a very significant impedance spike. Now why is that important? Well, it's important because these traces, when we're trying to build controlled impedance stuff, those things typically look like 45, 50, 60, 65 ohms, something like that. So that would be a normal thing. So if you could imagine putting a resistor in line that looks like 120 ohms, do you think that would have an effect on the circuit? Absolutely. So consequently, if you are going from layer 3, which is referenced to ground, to layer 6, which again is referenced to ground, but you don't have any stitching vias tying ground to ground very close, then you could very well have this situation. Now, is that problematic? Absolutely, that's problematic. Now, let's change the scenario a little bit, and let's put one ground to ground stitching via reasonably close to the signal via. So the signal via is going from this layer to that layer, and now we put in a stitching via, one single stitching via, close enough to it so I provide a closer path for the return current to move from this ground plane to that ground plane. Now that is the yellow situation. So if you look at the yellow here, you notice that I don't have nearly as bad a problem, and as a matter of fact, up to a gigahertz, I'm adding less than 10 ohms, worst case, into the impedance of that trace. So consequently, this is a much better behaved signal. But on the other hand, if I was doing SERDES work or gigabit serial or PCI Express, 10 gig Zowie, anything like that, these impedance poles are also accompanied with big phase shift reversals, and that will drive the input receive clock absolutely crazy if you're doing, high-speed SERDES type work. So there's the yellow. This is where I've just got one stitching via close. Now on the other hand, if I put 4 around here, where each one is the same distance as the original one, now what I've got is the red line. Now if you look at the red line, it's going up through 1 gigahertz. It looks smooth. It's going up through 2 gigahertz. It's still smooth. 3 looks smooth. 4 looks smooth. 5 looks smooth. And the fact that it is turning up is just a reflection of the fact that that via looks like a little inductor. It's thin and it's got length, so it looks like a little inductor. So what's the takeaway for this part? Well, the takeaway for it is that return current is real. You have to provide for it or you will have difficulties, and providing for it basically means you're tying this ground plane to that ground plane. Now let's look at a different situation. In this case, instead of having a signal reference to ground on both sides, I've got it referenced to ground on one side and it's referenced to VCC on the other side. So if you take a look at this, what I've got are two different stitching vias. One is a stitching via that's sitting out here. Not stitching via, but vias. I've got one sitting out here, which is this via 5, and it's a long ways from the capacitors that tie ground to VCC, because I can't use a stitching via when I'm changing the voltage of the reference planes. I have to put capacitors between these things. We call them bypass capacitors. So here's the 6-layer board, so I go signal, ground, signal, and then signal, power, signal, typical 6-layer stack up. That's what the stack up was. And so I'm going from layer 3 down to layer 4. Layer 3 reference to ground, layer 4 reference to VCC. And the first situation is in purple, and that is via 5. And when I look, this little dotted thing here, this is kind of a picture of a printed circuit board that's about 6 inches by 6 inches. And I've got a whole bunch of capacitors over here. I've got a 5 by 5 array of capacitors here. And then this via is away from the capacitors. And again, I'm seeing a similar sort of impedance spike, because as I go up in frequency, I do not have a good path for the return current to move from ground 1 down here to VCC. Now, I've got a second situation, and that's this red line. And the red line, if you could barely see it, that's via 2 right there. So it's right in among this 5 by 5 array of 0.1 microfarad 402 capacitors. And so it is among these capacitors, and you'll notice that the frequency response there looks much, much better. I don't have the spike at about, I don't know, 200, 350 megahertz, whatever that is. Oh, 200, 300, 350 megahertz, 360 megahertz. So I don't have the problem there, and indeed that line looks smooth until I get up north of 2, 3, 4. At about 4 gigahertz, you see the first resonant peak here that'll start potentially causing problems. So again, when I go through a via, the problem is not, quote, the signal current, because I know where that is. I have intentionally put in that via. The problem is understanding how does the return current move from where it is to where it wants to be. So again, signal integrity, electromagnetic compliance, training for mere mortals. More information on SIEMC.com. My goal is to teach everyone in the universe how to design high-speed mixed signal electronic systems that work reliably at full speed and pass FCC and CISPR tests on the first try. So thank you.